Hello again, right? So I hope you enjoyed the networking break. Hope you got to hear some new ideas and talk to everyone about building LoRaWAN solutions. So let me introduce you some things we were working on at IRNAS and solutions we built with LoRaWAN for various more unusual and then exotic applications. So allow me to introduce myself. So my name is Luka Mustafa. I am the founder of Institute IRNAS and Fabricor, and I'm pretty much interested in telecoms for quite a long while and have been working in this field for very different projects, from community wireless networks. About 10 years ago that was a big topic. Now LoRaWAN is coming up pretty much in the same range. And at Institute IRNAS we build well-tailored solutions for very specialized projects. So that typically looks as you will see in all the projects we'll be presenting later on today, that we take specification from one of the clients and build a specialized batch of devices, doing some very cool things. So we work in a number of different fields on the wireless optical communication as one of our specialties, on IoT devices, and in more research stream on 3D bioprinting and some cool applications in that direction. So today we'll be showing more things that are happening on the IoT front, as that's the focus of the conference, but also feel free to stop by our booth there and talk to my colleagues about any other topics you might be interested in. So what we do in a small and compact team is full-rounded engineering on electronics, mechanics, prototyping, and the system deployment. So we generally don't build platforms and cloud solutions, but devices to the cloud essentially. So you've met some of our team around the venue today doing various different tasks, but feel free to have a look if you want to speak to them, as they're all the engineering stuff, and you can ask questions on the topic about our projects if you are very much interested in that. So what we do and where we do it is we have the offices here in Maribor. That's why also the conference is here. And we have the whole production floor with machines for mechanical production, prototyping, and a lot of the hardware we're showing here is built with our facilities, and we really do fast turnarounds on prototype IoT projects for specialized applications. So we work with startups and some companies, really taking ideas, no matter how crazy they are, and turning them into proof of concept products, or to turn them into specialized products in batches of a few hundred devices before transitioning them to our partners that take this to a larger scale. So some of our customers are here. There's plenty of others that we work with, and we provide the engineering services for them, and they're from various different fields. Quite a few from more the agricultural IoT area, some in the nature conservation field, and some others like in the devices for cell cultivation, where we provide the IoT part, sensor control, and things like that that I will introduce in a moment. So the IoT devices we're working on, we're pretty much agnostic of different technologies. So we work on NB-IoT, LoRaWAN, and others as well. But LoRaWAN is really the most appealing technology for the majority of projects we build for our customers. As mentioned earlier today, it gives really good flexibility in terms of building your own network wherever in the world it is. You can extend it, build it, make it private or public, whichever way is very much optimal. Quite some interesting things we build are also underwater sensors, especially for animal tracking and some other monitoring that will be underwater for the majority of time, then come above water and start transmitting a LoRaWAN. And also one of the upcoming streams is edge computing, where you actually do a lot of computation, take images and create quite some data on the edge on the device, but because you have limited connectivity, you just calculate the answer and you send it through LoRaWAN. So completely in a different field, but where we are very active, is wireless optical communications. So we are best known for the Kurusa project you all might have heard of. This is wireless optical communication, much faster than LoRa. It does 1 or 10 gigabits in reasonably short distance of 150 meters. So this is to build fiber networks building to building in cities. And that's one area we specialize in, and the other one are more IoT devices. So in the past, we worked with SolarCast, and this is the largest citizen science group that does radiation monitoring. So we were building SolarCast devices, as you can see here. So autonomous sensors for air quality and radiation connected via 3G and LoRa. So they're now more used in the Fukushima area in Japan, monitoring the radiation, pretty much the nature recovery in the area after the disaster, and in the Los Angeles area with all the forest fires. One of the big topics is animals as sensors for us. So one thing is just conservation of animals, just trying to understand how they behave and all that. But actually, by doing so, you can get answers about the environment. So just a few cases, if you monitor penguins in Antarctica and they don't show up that year, or you see the difference in population in certain areas, you can see what's happening with the environment and the global warming and how that affects them. So, indirectly, you actually monitor all of those effects. With, for example, sea turtles, yes, first thing is obviously conserving the highly endangered animals and figuring out how they move and how they behave. But actually, with the camera systems we've built, they're used as sensors to detect how much plastic and trash is in certain regions in the ocean, and that is then analyzed to firstly detect where that waste comes from and what can be done in the environment to monitor that. So we build IoT solutions really going from Antarctica and penguins, very cold regions, to say Madagascar, where we have devices for river monitoring, where again it's for some endangered species of fish, where when the water runs out, someone goes there with a bucket, picks the fish, puts them in a pond, and when the water is back, they return them to the river. Since there's a few hundred specimens of that type of fish left, so it's really worth the effort in that case. In more tropical regions, in Peruvian forests, we have a network with base stations and plenty of sensors for animal movement and other detection via satellite link, of course, in that case. And in Africa and also in Cyprus here, in Europe, the turtle trackers we built of this sort are using sea turtles to monitor their behavior. And I'll tell more about that project and how LoRa is used in that particular case. You can see all of this hardware outside our booth, so feel free to be curious about it. But to be able to build all of these solutions for a number of our clients, we had to build some building blocks, especially for the edge computing devices where we typically have a Linux embedded system. We need to schedule power because there's definitely not enough power available, even with some smaller solar panels, to keep it running all the time. So we've developed a solution which we call Pira battery pack. So it does solar charging, real-time clock, has LoRa connectivity, and in the latest version also Bluetooth low energy. So with that we manage high power loads, but because this is LoRaWAN connected, you can instruct it remotely to turn on and off, change the schedules or any aspect of that sort. But at the same time, it allows us to very quickly build specialized systems and proof of concept deployments for a number of different applications. And here you can see that it's really used in a lot of devices at the same time, and being open source at the same time, so everyone can use it and build their own projects based on this. So diving deeper into the solutions, we have the Aribada turtle pit stop tags come in two versions or flavors. There's the GPS only tag, which is meant for tracking. What it does when the turtle swims to the surface, it captures the GPS signal within about 1.5 seconds, as well as the upcoming version now will have LoRaWAN, because at the same time you will try to transmit, because it's very likely that you have the animal in the region, around an island or something like that. So you can do some very coarse localization. You see on which base station it shows up if you have 4 or more base stations gateways around an island, for example. Or if you have proper geolocation in place, you can do very good tracking with that. And the interesting part is LoRa transmissions can be successful even a few centimeters underwater. So you don't need that good of a clear sky view as on GPS to capture the location. if you're sufficiently close to the gateways. So that's very good, and also you get some real-time information. The camera units are used in a different way, where you put this on a turtle in the nesting season, so it goes out to the sea for about 2 weeks and then comes back to the beach. And while it's out there, it records videos and we get all the data back. But the key part is when the animal comes back to the beach, you need to know it's there so you can go collect the camera before it swims off for another year or two. So you really don't want to miss that opportunity. And the basic method is have a guard walking up and down the beach, but that's a sandy beach of about 2 kilometers long, and you only have so many people. So it's good to know that 100 turtles showed up, 2 have camera. Now you need to know which of the 2 are in complete pitch dark, and LoRaWAN is quite a nice solution for that. And what's inside is actually some batteries, an embedded system, power management, LoRa, even wireless charging, and everything put in a case that works to about 500 meters depth, no problem for this particular solution. Almost the same approach as with the cameras in the Peruvian jungle. So there we built an arboreal monitoring system for the Aribada initiative, where the cameras will be on for the majority of the day, waiting for animals to pass through the canopy, take some photos, and then once in a while they will send the data back through the Wi-Fi backhaul network to the base station and then via the satellite uplink. But because Wi-Fi is very power hungry and wasteful, you can't have it on all the time. And LoRa you can easily use to schedule all of the devices to turn on at the same time or when you need them. But it allows you to do much more. Because if you have, say, 1 camera on a tree, you can have about 10 or more LoRa sensors in the area, just observing the general activity of the area. And only when you see some activity, you can turn on the camera to be ready and wait to capture some action. So some really smart things can be done with this to optimize the power consumption. In the Madagascar case, as I mentioned, it's quite a bit simpler. You hang this above a river, it will take the river level with the ultrasonic distance sensor. It will capture images, and then we'll send this, in this case, either via Iridium or LoRa, whichever is available. And we always want to use LoRa because it's much, much cheaper than Iridium connectivity. The interesting part also with the images, because you can't send images over LoRa, they're simply too big, is you can do edge computing, you can run TensorFlow and things like that, compute an answer, and then send pretty much the guesswork from that answer across, which is real time and gives reasonably good results. Like the basic one is you can count cars that way. If there's enough power to run a camera, with that you can count cars with reasonably good precision with the latest algorithms. And there's no need to send images or anything across. You only need to send every 5 minutes how many cars you counted, as the very, very simplest example. And a lot more exotic things can be done that way. And for example, our partners at the London Zoo are building something called Instant Wild, which does machine recognition of animal types. So you can say, I've seen 3 bears, 5 squirrels, and something along the lines. Very much as an example. But something like that is really an opportunity now with technology we have at hand. So the assembly of the system, again, very similar to what you've seen before, only we add some solar panels. And this, for example, there's enough capacity to boot up the embedded system and take about 20,000 photos with a full charge of the system because of a very quick boot time. And if you can process the photo and create an answer, you can send that at the same time, no problem. We've built a system of the same version, slightly modified for the Antarctica. So here it's taking photos of penguins, more or less. So it will take a photo every hour or 3 times a day, depends on the season, or it does it automatically. The more power is available, the more photos it takes. The difficult part here is that these devices are in Antarctica, and that means it's 4 flights, 5 days at sea on a ship, and this is just on the edge of Antarctica. It's not even that far down. So it's the only option to get there is once a year, more or less, when the tourist cruises have 1 spare cabin for researcher, which takes this there. So you get there, you place the cameras, you come back a year later, you collect them, and then you need to process all the data. But your data is a year old. You don't see real time happening. You have no indication of what's happening that season. So having LoRaWAN in such a case, and in the upcoming version we're doing exactly that, LoRa connectivity can be done between the cameras, and hopefully at one point a gateway can be introduced either with a satellite backhaul, or in the future years of technology like Thomas is developing and will be introducing a bit later on might be very handy for such an application. So the construction again is very simple, plenty of batteries, camera, power management system, LoRa module. You can add an external antenna, and that's it. So it's very straightforward to build devices of this type today. On a completely different field, which at the moment has nothing to do with LoRa, but there's interesting options for this, is we worked on angel shark tracking. So this is how to attach a tracker on a shark swimming underwater, or in the base while it's underwater. So we've developed a mechanism which currently attaches an acoustic tag of this sort. But so how this whole system works is you attach this acoustic tags to the fin of the angel shark. It swims around, and there's hydrophones in the water that are collecting those measurements. So with all the edge computing and processing that can be done now on the buoys, this is all moving in the direction where LoRaWAN can be a solution, where you can have a number of buoys again around an island with acoustic to LoRa conversion essentially, and you send data back in real time. Because again, at the moment this is done with huge storage. You place it there, you come pick it up a year later, and then you only see what's happening, which is a very long turnaround time if you have a 2-year project or 3-year project. You need to show some results. So with LoRaWAN, we can get a lot of more instantaneous results in this process. So obviously, why use it? What are the key challenges we've discovered on the field? So firstly, devices need to be very, very simple to use by untrained professionals and people that don't have technical background. So it needs to be zero config and simple interface. Like if you need a user interface, Bluetooth Low Energy is these days the simplest, because you can configure devices like turn on twice a day. You can easily type that in through the Bluetooth interface once you're installing it, or see if it's connected or something like that. And the cost of implementing that in electronics is quite minimal at this point in time. The real-time information is very much interesting. So we can have a look at this from like 2 levels essentially. The basic one is, does the device work? Because if you spend all the effort going in the jungle somewhere, putting a device there, then you have the issue, like you need to come back in 3 months and collect the data. But what if the device stops working after a week, or something happens, like a tree falls on it, or whatever bad happens to the device? You probably want to know that so you can go fix it, even though if it's recording all the data locally. Or for example, if you have a battery powering up a camera system somewhere, you at least want to know how much battery there is. So if it runs out, you can go and replace it. So that's quite simple to implement on LoRaWAN, and it's really straightforward, doesn't take that much extra power, and you add small devices to it. In the second, more advanced option, you also try to send that data via LoRaWAN, depending on the data type. For simple sensor measurements, that's straightforward. For camera images and larger batches of data, you need to be a bit smarter about it, but it's still very much possible with this. And also, it's hard to predict in a lot of cases what you want your device to do. So maybe you want to try different schedules, you want to try different settings. So you can think of LoRaWAN, if nothing else, just remotely being able to change settings of the device. Say if we have a bear trap, you want firstly, try to see how many images do I get. So while LoRaWAN, it will say I have captured 5 images today. From that 5 images, you hope you have 5 images of a bear, but if you get the result back, hey, I got 5,000 photos today, it's very unlikely, that's good activity. So you can tweak the settings or, change whatever remotely without going somewhere. And you can do the experiments with full remote control that way. And on more the deployment side of you is the network coverage map. So the difficult part is always when deploying networks in very rural areas, very remote, is what is the coverage? And this is one of the solutions we built for using LoRaWAN. So I mentioned how we use this technology, and I'll show how we actually test the coverage. So we've firstly had to solve the gateway issue. In a lot of cases, we use very simple gateways, the same construction that you will see in the workshop later on today for the ones that are participating, as we really want the liberty to have full control of the gateway, as we might want to do other processing. And with, for example, V3 coming up, we can do a full stack on the gateway directly, which is very nice for offline applications and things like this. And there's a more advanced gateway which we use quite extensively now, is the LoRaWAN. So pretty much the same version as the DIY build, but this one is certified, so you can best use it in projects where you need to buy a certified piece of equipment, which is really for most of the projects. So you can get in touch if you need something like that from us. Now the technical unknowns in deploying LoRaWAN networks are the following. So obviously, what is the coverage of a gateway? This can be quite well simulated for cities. This can be quite well simulated if the gateway is in a reasonably good location. But what if the gateway is like 3 meters down from the top of the canopy of the tree? There is no way you can simulate that. There is no way to know what the coverage of that gateway will be without actually testing it in the field or adding extreme margins and having high gateway density. So we want very simple methods to determine this. So we built a solution called drone mapping using the TTN mapper. So we put a LoRaWAN device on the drone and fly around. So in the simplest case, a nice field, you place a gateway in the middle of the field, you can fly around in a pattern and you see what the coverage there is. So the key part for it is if you want to optimize battery life, and that really depends on the spread factor of the devices. If it's communicating at SF12, you are using almost 100 times the power because the on-duration, transmission duration is long. So depends on the device construction, but you can, from a device that's supposed to last 10 years, get only half a year of battery life just because of poor coverage in that case. And from that reason, it's really worth investing a bit more in good network deployment, because in the long run you save the amount of money someone going out there and changing the battery. So this is the very simplest use case for it. The second one is seeing how well your gateway behaves and what's the shape of the coverage. So we've done some simple scans here. This is the same piece of land, just at different heights above ground. And we can see the signal based on the gateway, and you can see that it's reasonably omnidirectional, but there's quite a bit of power pointing upwards. And that's generally not optimal for your gateway because you don't have devices above you. They're sideways, so you probably want to have a more omnidirectional or a better antenna in that case. The more advanced use case of such a technology is actually you deploy a gateway and then you do a 3D scan with a drone of the radiation pattern of that gateway, meaning that you can see all the distortions because of the metal pipes, boxes, cables, poor installations. You can actually verify what the radiation pattern of the gateway will be, and even furthermore, you can use that in simulation software to determine how well the coverage will work. And you are used to seeing such diagrams if you ever buy antennas. You have the radiation planes, and here we've just done a scan of 2 different ones. You have the quarter wave omni antenna, DIY build, so you see some distortion here, but this is the antenna measured, fully deployed in a field on a pole, and a collinear antenna with some side lobes. But you quite well see that here a lot more power is directed on the ground level, left and right on this one, whereas this one omnidirectional points upwards quite a lot, which is generally useless if you're on a flat field because your devices are not above you, as mentioned. So here we've used the same approach to compare antennas, because you can really buy a bad antenna for LoRa. That's it's very good to know that there's plenty of very bad antennas out there, and it's almost a shame to call them antennas in a lot of cases. But we're just comparing here some known antenna, so reasonably good 3D omni antenna, with the key result of in the middle where there's the gateway, there's not much power being radiated up, so the antenna is not pointing upwards, to put it that way. versus a no-name helical antenna where we see that there's a lot of power pointing upwards. So the antenna is very bad in the directions where we have our nodes. And with this mechanism, we can really see immediately and very clearly what's happening in a given case. So just to wrap up this part, we use this, for example, in forests, where you place a gateway, you can fly on the canopy level and you know what the coverage there is. Because also climbing up a tree and trying if your sensor will work there takes a lot of time and is expensive. So you can say it's 100 euros per tree just for the climbing effort. But with a drone you can fly across 100 trees today. And an even more advanced use case is you can put a gateway on the drone, place the sensors wherever you want them, and then fly the gateway around until you find the optimal position for the gateway. That can be, say, select which tree you want to put it on, or select which corner of the building you want to put it on, and then make the decision without going there, trying it out, or huge signal margins to make sure you compensate for all the random effects in the nature. And something really exciting that we started working on just now is with IFREMER, a French marine organization, to develop sensors for sea buoys to monitor the swell, so the wave height essentially, and water quality, and report this through LoRa. And over the sea you have reasonably good coverage, up to 50 plus kilometers around an island if you have a good, well-placed gateway. So you can have quite a lot of that buoys around. And an even more interesting case is fish tracking. Like, obviously you think like you can't use LoRaWAN underwater, but this is not exactly what's the case here. Because you put the tracker on the animal, no, this is a large tuna fish, which is 100 kilos easily, so that there's no problem putting something on it. It will swim around for a month or two, then the tag will detach, floats to the surface, and just keep floating on the surface, and then start sending data through LoRaWAN. So this, I hope, gives you quite some insight in what we do. We have very exciting, very interesting projects. There's also plenty of more industrial use cases, which we can't share that publicly with you, but yeah, you're also welcome to join our team. And that's it for me. Any questions at this point?
Any questions for Luka?
So when you are deciding where to put the gateway or the sensor, let's look at the sensor way, the way of positioning. How much of level, so the RSSI level margin are you using? For example, you want to have a relatively successful connection all time. What kind of margin do you take?
Right, so the easiest way to do that in LoRa without knowing anything about signal levels and dBs and all of that is if you have all your sensors communicating on SF7, whatever happens in the environment is a good chance they will come through on a bit slower modulation rate like SF12 from that direction. And that means essentially if you have all the sensors running on SF7, they're very power efficient at that point. And that's the ideal use case. So in placing the gateway, obviously you want to receive all the data, and you will generally receive 90+% of the data if you discount for some random errors if you plan for SF7. So from the signal level, it's a bit more difficult to say because you really need to look at signal to noise ratio based on the environment to see what's there. But if you just look at the modulation rates, it's pretty much intuitive what's coming through. I hope that answers your question.
Yes, thank you.
Any other questions?
Any other? Okay.
How much does the weather, for example, rain or snow, affect the range of the antennas in the gateways?
Right. So again, that's reasonably difficult to answer. So the question was, how much does the weather affect the performance? So in most of the cases, we couldn't see very well defined weather effects. So frequency-wise, in the 868 and 900 megahertz, it's reasonably low. So it's well below gigahertz, and the weather effects will be quite minimal in this case. If you go to 2.4 or 5 gigahertz and onwards, you see quite noticeable effects. On very long links, you might see effects, but also due to the change in propagation. So not the actual attenuation direct line of sight, but you can get propagation, say, between the Netherlands and the UK, where you have sometimes a bounce of the signal, and you can get some really long distances. But these are like false positives, not very much in the false negatives direction.
Okay.
Any other questions? All right, perfect. Thank you very much.
Thank you.